Bismillahirrahmanirrahim. Welcome to lecture number 18, Digital Signal Processing course, Spring 2021. In the last lecture, we were discussing about the rough magnitude plot using the Z transform. Today, we'll continue our discussion on the same topic, but we'll see it in a slightly different way. The objective of today's lecture is to design notch, low pass, high pass, or band reject filter using this similar same concept. So let's quickly review two examples from the last lecture. If you remember, in the last lecture, we said that if we have a very simple system having single zero, we can plot its magnitude response exploiting its Z transform. So we are given with Z transform expression h of z 1 minus 0.75 Z inverse. When we plot its pole zero diagram, we'll see that there will be a pole at origin and there is a zero at 0.75. So when you plot the magnitude spectra of this system, you will get this response. So you have a minimum value at omega is equal to 0. So this is omega is equal to 0 and this is omega is equal to pi. So you have minimum value at omega is equal to 0. It is 0.25. How you write it? You write it h e to raise power j omega min, and you will get it is omega is equal to theta, and in our case theta is 0 degree. So we will get if we draw a vector from here to here, so this would be a vector from this one, and let's call this vector as r1 mod, right? So we can say that this is r1 mod and this is equal to 0.25. And when you have the maximum value, you will draw a vector from here to here. Let's call it r2 mod. So your maximum value would be h e to raise power j omega max. That would be equal to r2 mod, and that is equal to 1.75. Yes, clear hai beta? It's okay.
Yes, sir.
Okay, next, if we bring the zero, same system, but we are bringing the zero on the unit circle. So this is a case. So in this case, you have one pole at the origin. It's negligible. Then you have a single zero at z is equal to 1. This is omega is equal to 0. And if you try to plot its frequency response, so you can get the frequency response like this. We know that our frequency response will be like this. We have a minimum value at omega is equal to 0 because angle is 0, and we have a maximum value at omega is equal to pi. So how you find the response? It will be like this. So it's 0 at omega is equal to 0 and maximum 2 at omega is equal to pi. So h min of z would be equal to 0. H max of z would be equal to 2. We already knew about it from the last lecture. So it's been that whenever we bring a 0 on a unit circle, it will eat up that particular frequency. So let me take example number 3, in which we try to bring the pole in the complex domain and try to find its response. What would be the magnitude spectra of this system? 0.6 e to raise power j 5/4. We already done this in the last lecture as well, so that's why I'm quickly covering this. So I need to bring this in power, and I need to add minus sign here, right? Let me little bit zoom in this. So if you are given with this system, example 3, Your system is like this. So can somebody give me idea what is the magnitude response of this system? Anyone? Let me first draw its pole zero diagram. Its pole zero diagram will be like this. So you have one pole at zero at 0.6 and its angle is 45 degrees, right? And you have a one pole at the origin. So this is your pole zero diagram for this system. And if you plot the magnitude spectra, it will be look like this. Now you it's not 0.6. Control Z Z Z Z. Let's bring it in next page as well. Example 3. And let's make it 1, not 0.6. 1 e to raise power minus j5 by 4 z inverse. So still we have this 0 on a unit circle. We have this system on a unit circle. So if we try to draw its pole zero diagram, it will be like this, but on angle pi by 4, because now we are given information of the angle as well. So if we try to plot this system, we will have pole zero diagram. Let me draw first pole zero diagram, and then I'll draw magnitude response. So let me say, if I draw its pole zero diagram, it will be like this. It's z is equal to 1 and theta is equal to pi by actual z mod is equal to 1. Right, and you have one pole here. Now if I want to draw the magnitude spectra of this system, it would be like this. So now what in our case, this would be omega pi by 4, and let's assume this is omega is equal to pi pi by 4, pi by 4, and let's assume this is omega is equal to 5 pi by 4. So its minimum value would be 0. So your frequency response would be look like this. Exactly 0, and then it is 2 at omega is equal to 5 pi by 4. This is 0. So this function as minimum value h e to raise power j omega at minimum at omega is equal to theta, which is equal to now pi by 4, and that is equal to 0 because it is on a unit circle. And if something is on a unit circle, we'll get 0 because we don't have any vector. And if you want a maximum value, h e to raise power j omega max, so you will have omega is equal to pi plus theta is equal to pi plus pi by 4, which is equal to 5 pi by 4. And your value is 1 plus r, the length of r2, and let's draw r2. R2 would be this one. You need to draw this vector from the location of 0 to the point where you are calculating the frequency. So this is a point where you want omega is equal to 5 pi by 4. So the length of this is r2, and you can clearly see the length would be equal to 1 plus 1 is equal to 2. So that's how you see this, how this response behaves. So what this system is doing, this system is basically filtering the frequency contents of pi by 4. Let me write in text as by observing magnitude response h e to raise for j omega mod, we can say that this system will block only frequency content of pi by 4. तो यहाँ से नजर आ रहा है कि जो आपकी फ्रीक्वेंसी है इसको उसका जो पाई बाय 4 का कंटेंट है उसको ब्लॉक कर दे. That's why we can say that this is a notch filter of frequency pi by 4. तो हम ये कह सकते हैं ये नॉच फिल्टर है जो pi by frequency की ब्लॉक कर रहा है. तो व्हाट इज अ नॉच फिल्टर? नॉच फिल्टर इज अ फिल्टर notch filter sorry notch filter is a filter notch filter blocks particular frequency content in your signal. वो क्या करता है एक सिर्फ एक स्पेसिफिक फ्रीक्वेंसी कंटेंट्स को ब्लॉक करता है. दैट इज डिफरेंट फ्रॉम बैंड रिजेक्ट. बैंड रिजेक्ट क्या करता है वो एक बैंड को रिजेक्ट करता है जबकि ये एक पर्टिकुलर फ्रीक्वेंसी को ब्लॉक करता है. So we can say that this is basically a notch filter that filters the frequency content omega is equal to pi by 2. ठीक है बेटा? Any confusion? Any confusion?
No, sir.
Okay. So this filter, this is basically a notch filter. So try to let me give you a practice problem. Try to do it by yourself. Practice problem. Design a notch filter that blocks block frequency content of frequency 3 pi by 4. तो आपने एक सिस्टम डिजाइन करना है नॉच फिल्टर डिजाइन करना है जो कि 3 पाई बाय 4 की फ्रीक्वेंसी को क्या करे ब्लॉक करते हैं. ठीक है. सो हाउ यू डिजाइन दिस? एनीवन? Anyway, try this by yourself. Let's try to find design example number 4. Design roughly a low pass filter that block frequency content beyond pi by 4. तो आपने अब नेक्स्ट टास्क है हमने pi by 4 से बियॉन्ड जो फ्रीक्वेंसीज हैं उन सबको ब्लॉक करना है और उससे पहले हमने फ्रीक्वेंसीज को पास करना है. आर यू फेमिलियर विद लो पास, बैंड पास, हाई पास फिल्टर?
Yes, sir.
Okay, so we need to design low pass filter and we are given with cutoff frequency. This is your probably a cutoff frequency and you need to design a low pass filter. So how easy to design a low pass filter? Let me draw a circle. Right. So since we are given pi by 4, so we can roughly draw this, that this filter would allow the frequency content till pi by 4, and pi by 4 से beyond ये सबको block कर रहा है, तो सारी frequencies को block करना है, तो just go there and place all zeros till pi. Why pi? Because pi is the highest frequency component in your signal. So this is a low pass filter from, this is omega is equal to 0, and this point is omega is equal to pi by 4. So this is a low pass filter because this is low frequency and this is pi is the highest frequency. Pi is the highest frequency component in your signal. Pi is the highest frequency component in your signal. For example, I would say that a Y signal as a frequency content is 4 kilohertz. So 4 kilohertz is equal to pi. And then if somebody asks you what is the value of pi by 2 of a Y signal, so that is 2 kilohertz. So what is the value of pi by 4? It is 1 kilohertz. So every different signal have different value of pi, pi by 4, pi by 2, and 3 pi by 4. You got the point? You got the point, beta?
Yes.
Yes, sir.
Okay. Let me roughly draw its magnitude response. So roughly, if we see its magnitude response, it would be like this. So let me consider this is omega is equal to pi. This is omega is equal to 0. So let's consider this is pi by 4. So till pi by 4, you have our frequency response. And then beyond pi by 4, you will have response like this. So this is your low pass filter. It needs some transition for practical filter. So this would be pass band. This is your stop band. So look how easy to get rough estimate about a low pass filter. Similarly, if you are asked to design a high pass filter, example number 5, let me quickly design high pass, band reject, and bass pass, and then we'll move to the system with single pole. So design roughly a low pass uh, FIR filter. I think if you add FIR filter, because in FIR filter we have only zeros. So FIR filter add kar le, so it would be more appropriate because we have no poles in the system. So this is only valid for FIR system. So design a high pass filter that allows to pass all frequency contents beyond 3 pi by 4. 3 pi by 4 is basically 180, 225, sorry, it's around 90 plus 135 degree. ऐसा ही है बेटा?
Yes, sir.
So it would be around 135 degree. Right? So आपने FIR filter करना है जो 135 डिग्री से बियॉन्ड सारे फ्रीक्वेंसीज को पास करें. So let me design this system or in Z domain first, and then we'll try to draw its magnitude response as well. This one. right? So what would be the value of 3 pi by 4? The value of 3 pi by 4 would be here. तो इससे बियॉन्ड आपके सारे फ्रिक्वेंसी कंपोनेंट पास हो जाएंगे और इससे पहले पहले सारे ब्लॉक हो जाएंगे. So it's a rough guess that its pole zero diagram would be like this. It has single zero at center, and this is a frequency omega is equal to 3 pi by 4. So if you draw its frequency response, it will look like this. So let's assume this is 3 pi by 4 and this is pi, and I said pi is the highest frequency component in your signal. So your response would be like this. You have 0 0 0 0 0 0, and from here you have frequency response 1 till pi. So this vector, this is equal to 1 and this is equal to 0. So this is h e to raise power j omega mod, and let's call it high pass. So this is stop band and this is pass band. This is your example number 5. Now let's take example number 6. Example number 6 में you are asked to design a band. You are asked to design a band pass filter. Now you need to cut off frequencies. ऐसे ही है बेटा, जब आप बैंड पास फिल्टर डिजाइन करते हैं you need to cut off frequencies. ऐसे ही है.
Yes, sir.
Band pass and pass FIR filter that allows pass all frequency contents between. Beyond नहीं आएगा, अब between आ जाएगा. You need two frequencies. Let's we assume it allows between pi by 4 and 3 pi by 4. Pi by 4 to 3 pi by 4. So it means it's from 45 degree to 35 degree. 135 degree. So from here we can see that its pole zero diagram would be like this. So pi by 4 to 3 pi by 4. So you just need to draw. This point would be a pi by 4 and this point would be a 3 pi by 4. So इसके दरमियान में लाउड है, बाकी सारे कंटेंट्स आपके पास क्या हो जाएंगे, ब्लॉक हो जाएंगे. So it's blocking low frequency, it's blocking high frequency, and like this. So this is omega is equal to pi by 4 and this is omega is equal to 3 pi by 4. So this is a band pass filter that allows the frequency content to pass between pi by 4 to minus pi by 4. So if we draw its magnitude spectra, so this is pi by 4, this is 3 pi by 4, this is pi, this is 0. So if you draw its magnitude response, this is omega versus this one. So if we draw the magnitude response, so it would be like this. ऐसे ही है बेटा.
Yes, sir.
Yes, sir.
So this is pass band, this is stop band, and this is stop band. How to design a band reject filter that blocks the contents between pi by 4 and 3 pi by 4. So statement is important because if you misinterpret the statement, your answer would be negative. Let me take example number 7. These things are not given in your book, but that is part of your design roughly a band reject FIR filter that allows, that blocks, not allows, blocks all frequency contents between 5/4 and 3/4. Now we are talking about band reject. Band reject means that is not allowing to pass this signal. So how you draw its magnitude, Z transform and magnitude spectrum. So first, so now we knew that this is omega is equal to 5/4. This is omega is equal to 3/4. Now we need to block this, so हम इसके दरमियान में 0 place कर देंगे. Rest all contents are passing. So when you roughly try to draw its magnitude response, it will be look like this: 5/4, 3/4, and then let's assume this is pi. This is he to raise per j omega mod. So its response would be like this. So this is stop band. Pass band. Pass band. ठीक है बेटा?
Yes, sir.
Yeah.
So hopefully the concept is very much clear to you, because from yesterday to till today we almost done 14 different examples. So if somebody has some doubt, he or she can ask me again. We can even think for repetition it again. Anyway, this is how you can design FIR filter. This is how you can design low pass, band pass, high pass, band reject, notch filter, uh, FIR filter. And in FIR system, we have only zeros. And if we have a pole, that exists only at origin or infinity. Now let's talk about poles. Rough sketch of magnitude plot when system have a single pole. अब हम दूसरी तरफ जा रहे हैं कि IR सिस्टम की तरफ. उसमें आपके पास अगर सिंगल पोल हो तो फिर हम कैसे इस चीज को हैंडल करेंगे. हाउ वी प्लॉट रफ मैग्नीट्यूड when we have the single pole in our system. So in case of a single pole, what would be the expression? So let's take a very simple system which have only one pole, h of z. H of z, it lies on real axis equal to 1 over 1 minus 0.6 z inverse. Right, so it's similar. Since we have done a lot with a single zero case, so we can do it very easily. I'll try to cover it in a quick time, so we can jump to next topic, which is all pass and minimum phase system. So now you can see it is not in numerator, but it is in denominator, right? So if I try to uh, draw pole zero diagram of this system, so it will be look like this. Let me draw a pole zero diagram here. So anyone can help me? Where is the pole located now? Anyone?
At 0.6.
Now your pole is locating at 0.6 and there is a 0 at origin. So it's a reverse system, sort of reverse system. So you have 0.6, now you have a pole and origin पे आपके पास 0 आ जाएगा, because आप इसको जब open करेंगे तो it would be z over z minus 0.6. Right, so what would be the minimum and the maximum value of this system? So for minimum, there is a difference. In case of a 0, on same angle we got minimum value, but in case of a pole on the same angle we got the maximum value. Right, कैसे? अब अगर आपने let me draw a vector from here to the point where we want to find the frequency. So let's assume this is your value vector p1. This is pole, so let's use p notation. So this is p1 mod. So we can say that h e to raise per j omega maximum. Now you get maximum value at omega is equal to theta. In our case, our theta would be equal to 0 and the value of r is equal to 0.6. So and we have angle equal to 0. So we have this is 0. So 0 degree पे हमारे पास क्या होगा, maximum value मिलेगी. How? This is equal to 1 over p1 mod. So what is the length of P1? If from here to here 0.6, from here to here it would be
0.4.
0.4. So it would be 0.4. So this is equal to 2.5, right?
Yes, sir.
So what would be the minimum value? तो यहाँ पे देख लें, जहाँ पे जीरो के केस में मिनिमम वैल्यू आ रही थी, यहाँ पे मैक्सिमम आ रही है, और वहाँ पे जहाँ पे मिनिमम आ रही थी मैक्सिमम आ रही थी हमारे केस में, वहाँ पे मिनिमम वैल्यू आई. So minimum value would be at pi omega is equal to pi plus theta. Pi plus theta is equal to pi plus 0 is pi, and that is equal to 1 over p2. Let me draw p2. What is the value of p2?
1.6.
It would be 1.6. This one, p2 mod. This is equal to 1 over 1.6. It is 0.625.
Yes, sir.
Now, if you want to draw the rough sketch of this system, you can draw it. It would be like this. So you have the maximum value at omega is equal to 0 and the minimum value at omega is equal to pi. The maximum value would be how much? It is 2.5. So response would be look like this. So it is 2.5, and at pi its response would be 0.625. So this is your h e to raise per j omega mod versus omega. Clear है बेटा?
Yes, sir.
Okay, next we solve a complex system. Let's bring the zero in the complex domain. Can we bring the pole on a unit circle? Let's try this. Let's try this and try to find the response at, this is example number 9. Let's try. It's not practically possible, but let's try. If we make it 1 over 1 minus z inverse, so what would be the value of its pole? What is the pole zero diagram? Pole zero diagram would be like this. This pole diagram would be like this. So you have one pole at here, 0 here. So what would be the maximum value? H e to raise per j omega max at omega is equal to 0 theta, and that is 0 degree. So this is 1 by P1. P1 is basically 0 because it is lying on unit circle. So 1 over 0 and it would be infinity. ऐसे ही है?
Yes, sir.
So this means, let me write in text as well. This means we cannot put poles on unit circle because they will make our response infinity. How you define infinity in our term? Or make system unstable. तो हमारे सिस्टम को ही अनस्टेबल कर देगा. So it's mean that we can say that this is not a valid system. We are not happy. Not a valid system. So we cannot place a pole on a unit circle. From this example, we clarify that we cannot have a system 1 over 1 minus the inverse. तो जहाँ पे भी आपके पास कोई भी एक पोल भी यूनिट सर्कल के ऊपर आया, that will make your response infinity. ठीक है बेटा?
Yes, sir.
Let's take example number 3. तो इस वजह से हम इसका बाकी जो है एग्जाम्पल 9 की है. Anyway, as this is example 7, 8, and this is example number 9. Okay, what about so if let's consider you want finding rough magnitude response at particular frequency. अब हम क्या कहते हैं, एक पर्टिकुलर फ्रीक्वेंसी, मैक्स और मिन तो हमने निकाल लें, उसके साथ हम एक पर्टिकुलर फ्रीक्वेंसी पे अगर मैग्नीट्यूड रिस्पांस लिखना चाह रहे हैं इन केस ऑफ पोल एंड जीरो बोथ. So let's finish this topic by having example number 10, last example, and with this example we will clarify multiple concept. Example number 10, let's have a complex system in which we have both zeros and poles. H of z 1 minus 0.9 z inverse. We have one pole here. Let's bring two poles in a complex plane as well. So let me write here 1 minus 0.7 e to raise per j pi by 4 z inverse, pi by 4 z inverse, pi by 4 z inverse. Z inverse, let me change z inverse. Let me drawing it here. X. Right, thanks, he accepted. So let's, because complex pole cannot exist alone, so let me make it reciprocate at plus pi by 4 z inverse. Let's take a 0 as well. Uh, 1 minus 0.5 z inverse, and let's take 1 0 at 1 plus 0.9 z inverse. Okay, let's take this complex system, and you are find frequency response, rough magnitude response at omega is equal to, let's consider 3 pi by 4. हम एक स्पेसिफिक फ्रीक्वेंसी ले लेते हैं 3 pi by 4 पे सिस्टम का रिस्पांस क्या होगा. Let's first draw the pole zero diagram for the system, and then from pole zero diagram we'll try to grab the concept that how we can draw a better frequency response using this pole zero diagram. Let me clear here this one, and here. So let's quickly draw together pole zero plot diagram. Let's draw it with red color. So we have 1 0 at 0.5, and let's call it 0.5, and we have 1 0 at 0.9. Since here is a plus sign, so it means that is on the left side, so you have another 0 at 0.9. This would be minus 0.9. You have one pole at 0.9 on real axis, so it means that you have a one pole here, and you have two complex poles, 0.7 e to raise per j pi by 4 and e to raise per minus j pi by 4. So it means that this is, for example, 0.7 and angle 45 degree, and this is minus 45. So this is your complete system. And where you want to find the frequency response, you want frequency response here at 3 pi by 4. So you are standing here, you want to look omega is equal to 3 pi by 4. So here, so this is the basic outcome of your system. So what you need to do, you need to draw the vectors from poles and 0 and divide the product of the zeros to the product of poles. How? Let me write a formula on next page, then I'll come back on same page for further clarification. And I think we can only do it today. Wait a minute. Okay, so let me draw the formula because we have two zeros. So let me draw the formula, write the formula. So I'm going to write formula h e to raise power j omega at omega is equal to 3 pi by 4. This would be equal to r1 mod dot r2 mod divided by, we have three poles, p1 mod dot p2 mod dot p3 mod. बात समझ में आ रही है? आपने लोकेशन ऑफ जीरो से 3 पाई बाय 4 तक वेक्टर ड्रॉ करने हैं जीरो से और पोल के, और उनकी लेंथ को आपस में मल्टीप्लाई कर दें. So let's try to do that. So if we have two zeros, let's draw zero with blue color. So we need to draw a vector from the location of a pole to here. Let's call this is R2 and we have another 0 here. We need to draw a vector here. Let's call it R1, right? So this how you get the value of R1 and R2. Now let's draw this with green color. This could be your P1 mod. This could be your P2 mod. And this could be your P3 mod. Since these are rough estimate, so let's roughly estimate the value of R1, R2, P1 and P2 and P3. So let's consider value of R1 from here to here would be 1.4. And what will be the value of R1? Let's assume it is 0.9 over. What would be the roughly value of P2, P1? I think it's around 1.9, I guess. What would be the value of P2? P2 is this one, so it's 1.3. And what would be the value of P3? I guess it's 1.7 around. ठीक है बेटा? So आप इसको multiply करेंगे, you will get net answer. So that would give you the frequency response at this system. अगर कोई multiply जल्दी कर देता है तो we will draw it quickly and we can conclude our lecture. So what would be the result of 1.4 into 0.9?
1.26.
1.26 divided by multiply 1 by 9 1 by into 1.3 into 1.7
4.199.
1.199 and then divide them
0.3.
0.32. Thank you beta. So this is omega is equal to 3 pi by 4. So now we need to draw a rough sketch of this diagram. So you can say that rough sketch of this one would be 3 pi by 4. This is pi by 2, pi by 4. It would be like this. So here you will get 0.32. This is omega versus He2 respectively. So that's how you will find the magnitude response. So if you have a two zeros or two poles in your system, you just need to draw the vectors from the location of zeros to the point where you want to find the frequency, and then you need to take a product. So in our case, we have a two zeros and three poles. So we draw the three vectors from location of poles and two vectors from the location of 0 to the frequency point omega is equal to 3 pi by 4, and then we take the product and divide and we will the final answer. So this is how you can find the rough plot. So from this article we learned about how to draw the rough sketch of the magnitude plot by exploiting the Z transform expression. So that is the sole purpose of your chapter number 5, because it give you a better insight into the properties of the system when you combine both uh, Z domain and the frequency domain together, right? So let's start, since we have 5 minutes. So let's start next topic, which is the all pass system. This is your article, I think 5.5, I guess 5.5, all pass systems. You can call them all pass filter as well, right? So in some books you will find all pass system, in some books you will read about all pass filters. All pass filter, as the name indicates, they have a linear phase response and they have constant मैग्नीट्यूड रिस्पांस. नजर आ रहा है ऑल पास का मतलब है कि सारी फ्रीक्वेंसीज को पास कर रहा है, किसी भी फ्रीक्वेंसीज को ब्लॉक नहीं कर रहा, राइट? फिल्टर्स के पर्सपेक्टिव में अगर देखा जाए. So if you want to write the expression for all path system, let me copy it from here. There is only one condition for to satisfy for all path system. All path systems say that Z inverse minus C conjugate, from where I can take conjugate as C inverse minus C conjugate over 1 minus C Z inverse. Let me write this condition for all real cases. This is the basic Z transform expression for all path system. Let me write here AP. AP stands for all paths and make it subscript all paths of Z. So this is first expression written in your book for all path system or all path system. And this says that if there is a pole, मैं ब्रैकेट में लिख रहा हूँ इनसाइड यूनिट सर्कल, अगर यूनिट सर्कल से पोल बाहर जाता है तो सिस्टम स्टेबल अनस्टेबल हो जाता है. If there is a pole at Z is equal to C, then there must be a zero. Must be, let me write, there must be a zero at 1 over C conjugate. So this is the only condition for all path system. It says that if there is a pole at C, there must be a zero at 1 over C conjugate, right? So expression is given here. Let me illustrate this with the pole zero diagram. What does it mean? And let's take an example, then we'll continue our discussion in the next class as well. So let me take a very simple system. Last minute. Right. So this property is saying that if you have some pole, let's assume at inside unit circle, so let's we have a pole at 0.5. So C is equal to 0.5. So what will be the value of 1 over C conjugate? So you can say real का conjugate आपके पास वही आ जाता है 1 over 0.5 conjugate, it would be equal to 2. So this is pole, this is 0. So if we saw a 0 at 2, so this will become an all path system. So we have to satisfy one condition. If there is a pole at C, there must be a 0 at 1 over C conjugate. And if I would like to write this Z transform expression, I can write it very easily. I know. Just first write 1 minus 0.5 Z inverse, because you have a pole at 0.5, and then you write Z inverse minus 0.5 conjugate. So this is this mathematical expression for this system. Right, so we just need to satisfy one condition. If there is a pole at C, there must be a 0 at 1 over C conjugate. I'll start from all path system from next lecture as well, so don't worry about it. So today we finish the second objective of this chapter, which is the rough sketch of the magnitude plot using Z transform expression. So with this, I'm concluding today's lecture. Let me stop the recording. Any question?